friend. Welcome. My name is Derek Harder, and in this video, we're going to continue talking about how the XV6 teaching operating system handles traps, but what happens when a trap, an exception, or interrupt occurs when we're already in kernel space. So we have to handle it slightly differently, as we'll see here. It's actually simpler in many ways. As we'll see here. So if you're ready, let's go ahead and begin and start talking about traps when they occur in kernel space. Okay, so traps that happen while we're in kernel mode are handled in a different way than traps when we are in user mode. So the stvec, remember that, I'll remind you, we'll look at this, but one of the things that happened in the uservec routine is that the stvec, the register that holds the place to jump to when a trap occurs, the trap vector, is changed to point to kernelvec. Okay? So when we're already in kernel mode, or when a trap occurs and we're in this kernelvec, we can rely that we're already in kernel mode, so we don't have to switch the kernel page, to use the kernel address space, nor do we have to change the kernel stack. Okay, so that's one thing that's easier in the kernelvec code. We don't have to worry about changing over to kernel address space or changing, so we're no longer using the user stack, but using the kernel stack. That stuff has already been done. But unlike for the user mode and on the trampoline, the kernelvec doesn't save the registers on the kernel stack in order to save the state and handle the trap. It saves the registers on the kernel stack instead. Okay, this makes sense if you understand what's happening here. The basic thing that we want to do is we want to allow a trap to occur when we're already servicing a trap. All right, so especially device interrupts. While we're servicing a device interrupt, a different device interrupt can occur, and we want to allow that to happen, to have nested interrupts being serviced. So that means, the trap frame, when we were switching from user mode to kernel mode, we only needed one of those, one place to save all the registers that we were using that we would ultimately restore when we switch back to user mode. But in this case, we could have an interrupt handler get interrupt by another interrupt handler, by another one, and by another one. So we could have multiple nested levels of interrupt handlers. So we need actually a stacked data structure. We can't have just a single frame, and we don't know how deep it might end up going. So we really need a stacked data structure, and that's the purpose of the kernel stack. One of the main purposes of the kernel stack that's defined for this is so that we can handle nested interrupts like this. And also, we will have to talk in more detail about some of the things that are supported by XV6 to allow for multiple CPUs. So for a multi-core system where we have more than one CPU, this allows to handle traps that occurred on a different CPU. All right. So another difference is when we're already in kernel mode, we don't have to worry about anything else except for device interrupts causing a trap. Right, so this should make sense again if you think about it a little bit. Obviously, we don't need system calls. We're in the kernel. The kernel doesn't need to change into kernel mode if it needs to do a typical thing like a system call does. Right. So and in fact, it won't need to do that. We just won't actually call system calls inside the kernel. But the other thing is that exceptions could occur, but if an exception occurs, that means that they usually really just can't be recovered from. So basically, if an exception caused a trap, we're just going to do a kernel panic. Okay? So in more complex operating systems, we might handle exceptions that indicate, that we're accessing memory while we're in kernel space, and we want to increase the kernel page table. So we want to dynamically allocate memory, but we don't typically do that in XP6, which is a simpler operating system. Okay. So before we look at the kernelvec, let me just remind you of a few things for the uservec that we looked at in the previous video. So for one, remember, we saved the state to the trap frame. And we never had to have more than one of those. We only needed to save one state when we were transitioning from the user mode to the kernel mode. The other, state for like the if the user process had called a function, they called another function, they called another function, that state is on the user's the user process's stack, but that's already saved in the user address space. Okay. Another thing that, so when we jump to usertrap, one of the first things that we did was we changed the stvec register to now point to the kernelvec. So we had to be careful to keep another trap occurring between when we entered the uservec. So remember, by default, the hardware disables interrupts, so no device interrupt can occur. We had to be careful not to do some. I mean, definitely, we don't call syscall by calling ecall, but we had to be careful not to cause an exception to occur. But after that, so basically at this point, any trap that occurs from an exception or a device interrupt is going to go to the kernelvec, the kernel vector. So the kernelvec RISC-V assembly code is in the kernelvec. So the uservec was in the trampoline.s, so that's the code for the trampoline page or the uservec page. The kernelvec is in the kernelvec.s. Okay, so it starts off looking kind of similar, but this is different. This isn't saving to main memory. It is, but this is saving to the kernel stack. Okay, so you might be familiar with manipulating the stack by, you push something on the stack, then you increase or decrease the stack pointer. So what happens in this code is it just decreases the stack pointer by the amount needed by 256 bytes because we're going to push on 256 bytes of information. And it's not pushing on all of the registers, only the registers that it needs to. Right? So that's another difference here. And I should have mentioned, or I should have reminded, so one of the things that happens on the trampoline page, if I remember, is we switch over to the kernel stack. So that's happening here. We're pulling off from the trap frame the pointer to the kernel stack for the process. We have to have a separate kernel stack for each process that's running, and that's what is loaded onto here. So that's all we have to do to kind of save state in order to be able to restore it when a kernel trap happens. When a trap happens in the kernel vec routine. And notice basically this is assembly code, but this is basically calling the C function called kernel trap here. And that's defined in trap.c, the same place that usertrap is. Okay. And before I jump to that, notice that, this is really just the reverse of saving this state. So when we return from handling the trap that happened in kernel mode, we just restore everything off of the kernel stack from whatever the stack pointer register is pointing to. And then we add 256 back to the stack pointer to move the top of the stack after popping all that stuff off of there. So the kernel trap C code is in the trap.c in the same place where the user trap was that we looked in the previous video. So below the user trap there's the prepare return, which was used by the user trap. And then we'll find the kernel trap here. So a few sort of sanity checks are done here. So this code should only have happened if we were already in supervisor mode. So the SPP should have been set to 1. So if it's 0 here, we just panic. And also, part of the trap mechanism is it should disable interrupts. So if somehow interrupts are enabled here, we just panic as well. So that shouldn't happen. Otherwise, we're using the same method that we saw in the user trap. We'll talk about this later on when we talk about device drivers and things. So this handles like interrupts from devices, and it returns which device did the interrupt. and then return 0 if it couldn't handle that. So, you know, if this is an unknown or something, again, we just panic. So that shouldn't normally happen unless something's corrupted or we've got a bug. A device type of 2 is actually a timer interrupt. So this, when we talk more about process scheduling in this class, we'll have to talk about this, but basically, if the, you know, what happens for doing time slicing is the operating system sets a timer interrupt to go off in regular intervals, you know, like 10 times a second or something like that. So if that is what happened, we're going to call this function, which is going to cause the current process, whatever current process is running, to yield the CPU. So basically to be interrupted involuntarily, and to be put into a state similar, you know, to be saved, similar to what happens when the user trap occurs. We have to save the process state, and then eventually the scheduler will get called so that we can schedule another process to restore it and let another process start running on the CPU. So apparently, as this comment says here, the yield could cause some other traps to occur. So the reason I skipped over these, but the reason why the S, you know, remember this is the return PC register, and the status bits. So we just actually save those in a local variable, and then restore those in order to get correct functioning for this kernel trap, just in case those got messed with from other traps happening in this yield call here. So the return from here will return back to the kernelvec assembly code, the kernelvec code here, right? So this call acts like a function call, and on return from that function call in C, we're going to be back executing instructions from here. So, and I already mentioned, right, this is really doing the reverse of what happened here. And then the final thing is that the S return is done again, right? So this causes the hardware, the corresponding, you know, hard-coded, hardwired things to be undone. You know, this restores the program counter and other stuff, so that we can return from this trap. Okay, so that's it for this video. A lot shorter than when we talked about, you know, traps happening when we were in user space. Just to summarize quickly some of the main points that we went over in this video. So traps are handled differently when they occur when we're already in kernel space. So there's a set of there's a kernelvec code, a kernel vector set of assembly code, and a kernel trap function that handles what should be done when a trap happens when we're already in kernel mode. So, you know, in many ways, it's simpler. You know, we can rely that we're already in kernel mode when executing the, you know, when a trap occurs and we start executing the kernelvec, right? So this is one of the things that happens in the user trap method is it sets stvec to point to kernelvec, right? And it has to be careful to not enable interrupts until that has happened, so that we don't end up jumping back to the uservec on the trampoline page, right? So, you know, remember the hardware disables interrupts, and the that code has to be careful not to generate an exception that would cause a trap until we've repointed the stvec register to the kernelvec. So, and kernelvec saves the state it needs in a slightly different way. It just pushes that onto the stack. So this allows for nested, interrupts to occur potentially. Also, for when we have a multi-core system, when we're supporting more than one CPU, this allows to handle traps that occur on different CPUs. And we'll have to talk more about that later on in this class. So really, the only thing that's expected to happen are device interrupts when we're already in kernel mode. So if we're in a trap, or in, you know, however we got into kernel mode, only device interrupts are what we normally expect, including timer interrupts, which are set up to be generated by the operating system. Obviously, we don't need system calls, so the kernel shouldn't be calling system calls. Other kinds of things usually are going to result in a panic. Okay, so anyway, that's it for our discussion about traps occurring when we're in kernel space. As usual, I hope you find these useful in understanding what's going on with our x86 operating system. Send me an email or let me know if you have questions or things. But that's it, and I hope to see you in future videos.